We're going to start this chapter just talking about the universal law of gravity. This is that law, if you remember from last year. G is the universal constant. That is the value 6.67 times 10 to the negative 11th. And R is the center to center separation distance. This law states that any two masses will exert a force of attraction on each other, and that force is directly proportional to the amount of mass, but inversely proportional to the square of the distance. Now, we're going to first apply this to the principle of superposition. What the principle of superposition is, it states that the net effect is the sum of the individual effects. Basically, if there's a bunch of particles within the same space that are acting on each other, the effect of that is the sum of the individual effects on each separate particle. I'm sure that didn't make too much sense. So if I have a particle here, another particle here, another particle here. So those masses are having an effect on each other. So that's mass 1, mass 2, mass 3. So if these particles were all freely floating in space, the principle of superposition will be able to solve for information to see how they're all going to behave together. Now, we're not going to look at any acceleration or motion with respect to these, but each of them are exerting a force of a gravitational force on each other. So a type of problem would be, what is the net force on mass 2? Okay. Now, if we look at mass 2, mass 3 is exerting a force to the right on mass 2. So we'll say that's the gravitational force of 3 on 2. And then mass 1 is exerting a gravitational attractive force to the left, to the force 1 on force 2. There's no other object that mass 2 is interacting with, so we've identified all the forces. Now it's a simple vector math problem, which is the force of 3 on 2 minus the force of 1 on 2, and that'll give you your answer. Where this becomes more of a challenge is figuring out what force 3-2 is. To do that, we would have to use the law of gravitation. So for F, the 3 on 2, you would of course have to use mass 3 and mass 2 in your equation. And I'll call that x, which will be the distance between those two. You would also have to do that for force 1 on 2. Again, the only thing that changes is the mass. I'll call that R. Once you have those two, you can plug that in, and you'll get your answer. More complicated problem would be, put a mass there, mass there, mass there. Mass 1, mass 2, mass 3. So now what is the net force on mass 2? So we still have to identify all the forces on mass 2. So mass 1 is now pulling it up, and mass 3 is pulling it to the right. And we end up with a two-dimensional net force, not drawn to scale. So here, you would really just have to find these each of these individual forces, and then Pythag and inverse tangent that. So, since each of those would just be an x and y component, the net force would be the vector sum of both of those. The only way to make that more difficult is to add more particles. More particles mean more forces. So if this was mass 2, and same question, what's the force on mass 2? So mass 1 is still exerting a force up, mass 4 exerting a force this way, mass 3 exerting a force that way. You would have to now sum up the forces in the x, where we have the force from 4 on 2 acting in the x direction, plus the force of 3 on 2 times the cosine of the angle that it's acting at. And that'll just give us the x components. You would then have to sum up the y components, and then, again, Pythag and find the angle, usually inverse tangent. Hopefully that's enough explanation for you to figure out the few problems that you're going to see like this. I don't think I have more than 1 or 2 on the website, and these types of questions only appear on multiple choice, usually more in concept. So that's really, I think, all you would really need at this point for the class. If you want to see how this gets more complicated with the calculus, continue watching. So in this example, we have a particle of, we'll say it's mass 1, and then we have a long rod that's one-dimensional in shape that'll have a mass of m2. Now, each section of this rod has a small amount of that mass, and each small amount of mass is going to interact with that mass 1. And as we move further and further away, each of those little sections of mass exert less gravitational force on mass 1. So if we wanted to figure out the net force on mass 1 due to that rod, we're going to have to use some calculus. Now, we know that the net force is the sum of all of the little forces due to the dm. So this mass has a force exerted on it by that little mass, so we get df between those. That mass with this dm, so we get a little force between those, and we add up all those forces to get the net force. Each little force is due to the universal law of gravitation, so it's going to be g times m1 times dm all over the location of dm squared. Now I have to mention that this rod is a uniform density, so that the lambda is equal to the total mass over the L, and that total mass is going to be the mass 2. That's going to be equal to, and since density is uniform, the small mass packet over its infinitely small location that it's at has to be equal to lambda as well. So since our function has an integration of all the masses, but the force function is a function of x, we're going to get dm in terms of x. So that's where we use the density equation. Solving this for dm, we get m2 over the total length times dx. Now that gives us, we can get rid of the dm. We substitute that into the integral. And dm becomes ml over the total length dx. Now pull out all the constants. So we have our function of x that we have to integrate. Now remember that we are integrating the forces between mass 1 and the first little packet of mass, that is a distance of a away, all the way up to the last packet of mass, that is L plus a away. So those are going to be our limits of integration. So we're going to integrate this from a to a plus L. The integral of 1 over x squared is negative 1 over x. And we still have our constants. And we are evaluating this between a and a plus L. So what we do is we just plug those values in, subtract them. So we have 1 over a plus L, and that's negative, and then minus the beginning parameter. So minus a negative is a plus, and it's 1 over a. Still all multiplied by our constants. So now I'm going to just move the positive in front and get it so that they have a common denominator. So now we can combine the top. A minus A gives me L. And if we look at our constants here, this L cancels out that L. And we're left with G, M1, M2, all over A times A plus L. And that is the net force. I did a bad job with keeping my equal sign throughout my math here. Now, I said earlier in the video that I haven't seen this applied here in gravitation on the mechanics test, but this type of integration is very common when we get to E and M.